So it's a great pleasure to introduce my colleague and friend, Ferenc Krausz. Ferenc is born in Hungary and is now a citizen of Hungary and Austria. He got his MS in electrical engineering in Budapest and in PhD in Vienna in 1991, his habilitation in 1993. Actually, it was in 1993 that I met him first, and from then on I've known him ever since. He joined the electrical engineering department as an associate professor in 1998 and a full professor in 1999. That was in the Technical University of Vienna again. In 2003, he was appointed director of the Max Planck Institute for Quantum Optics in Garching, Germany. And in 2004, he was also a professor and chair of experimental physics at Ludwig Maximilian University in Munich. His research, well, I don't think it makes sense for me to tell you about his research because he's going to talk about it right now. But suffice it to say that it's in attosecond photonics, and well, you'll hear about it now.
Thank you very much, Paul. Thank you for your kind introduction. Can you hear me? Is it okay? Yeah, okay. Good afternoon, ladies and gentlemen. It is a great pleasure and honor for me to be here and be allowed to give a lecture in this renowned symposium. It is a particular pleasure and honor for me to be on the stage in a session chaired by Paul, who inspired me and influenced my work like no one else. In my talk, I'm going to address latest advances in ultrafast laser technology, which now provide, for the first time in the history of science, direct access to Picometer-Attosecond scale electronic motions in all forms of matter. As you know, these electronic motions are ubiquitous, not just in physics, but way beyond the borders of physics in modern technologies, but also in life sciences, chemistry and biology. The applications did not quite reach out into social sciences yet, but we are working on that. The work I'm going to present has been done at the Max Planck Institute of Quantum Optics, and the chair of experimental physics of the Ludwig Maximilian University, both situated in the Garching campus of Munich, in the north of Munich, about halfway between downtown Munich and Munich Airport. Of course, the work that I'm going to present has not been done by myself, but a great number of fantastic co-workers as well as collaborators, whom I very gratefully acknowledge, whose contributions I very gratefully acknowledge here. Unfortunately, I don't have the time to name all of them, but I will name a few of them in the context of specific experiments. I would also like to thank Christian Hackenberger and WoogieWorks Animation Studio for the graphics and animations in my talk. What you see here is how the electric field of a fuse cycle laser pulse suppresses the Coulomb potential binding the electron of the hydrogen atom to the nucleus and allow this electron to tunnel through this narrowed barrier. Direct access to the electronic structure of matter in space and to its dynamic fastest dynamic changes in time, here represented by optical field-induced tunnel ionization, requires a resolution of about 10 to the minus 8 centimeters and 10 to the minus 16 seconds. Correspondingly, if we wish to make these atomic scale electron motions accessible to human observation, we need to create a device, we need to create tools that are capable of providing us with a temporal magnification of about 10 to the 16, which is about the square of the magnification we need to make atomic structures perceivable in space. Attosecond technology furnishes us with this tremendous magnifying power, as well as more and more also with the capability of controlling these motions on their natural time scales. So I will start my talk with just very briefly reviewing the basic tools and techniques. This is going to be a kind of warm-up for many of you, so I apologize to all those for whom this is rather trivial, so please consider this just as a warm-up for the rest of the talk. Then I'm going to address a few of the latest applications which center on electron phenomena in solids, and in the final part of my talk I will discuss a little bit, if time is left for that, a little bit the future of attosecond technology, which has actually already started. So attosecond metrology and control are intertwined, both requiring a force that is variable in a controlled fashion on the relevant time scale. The relevant time scale is the natural time scale of electronic motion. This is the attosecond time scale. So the electric force of light is obviously capable of providing us with this force, but only if its temporal evolution is well controlled. So what we need for this is obviously what we need for sort of providing this force is a laser pulse with a controlled temporal evolution of its electric field. Such laser pulses have become available quite some time ago, back in 2003, and opened the door to both controlling and measuring electron processes on their natural time scale. I guess one of the most spectacular consequences of this newly emerged technical capability has been the generation and measurement of isolated attosecond pulses. My apologies go to all those in the audience who have seen this movie already, this small animation already, but at least the music should also be new to them, so please just enjoy the music. So, by the way, it comes from Hungary. So this green cloud here represents the most weakly bound electron of the atoms we expose to a few cycle laser pulse. And as you see here, at the crest of the first intense half cycle, obviously the electric field becomes strong enough to detach this most weakly bound electron from its atomic binding with some probability. Of course, it goes, if the electric field points downwards, it goes upwards because of this awkward convention of the negative charge of the electron. And this process happens due to tunneling ionization. The strong field suppresses the Coulomb barrier, as we just discussed at the beginning of the talk, and the electron can tunnel through this barrier with some probability. So then in the first moment after this ionization, the electron continues its way. It's pulled away from the atom because the field still points in the same direction. But a little bit later, at this point, the field reverses its direction, pulls the electron back, and this freely propagating wave packet can interfere with the bound state portion of the very same electron, and this interference creates a tiny atomic antenna, as you see it here. This is actually the result of a quantum mechanical simulation. Here you see back and forth in time how propagation of this quasi-free electron wave packet across the bound state portion of the wave function of the electron results in interference between the two portions, and this interference makes the overall wave function oscillating up and down, forming a tiny atomic dipole, and this atomic dipole is radiating, and that's what results in this short burst of high-frequency light. This simple semi-classical picture was put forward a bit more than 20 years ago by Paul Corkum in a paper which has been cited, I guess, more than 3,000 times meanwhile, and forms the basis of an extremely powerful semi-classical theory for the description of this process, for the description of attosecond pulse generation. In a quantum electrodynamical framework, we might also argue that the electron that has been extracted from the atom absorbs a large number of photons from the strong driving field, and upon recombining back into its original ground state, emits all this energy in a single photon. So basically, the process converts many small energy photons from the driving radiation into one single high energy photon. And obviously, this high energy photon is equal to the sum of the energies of the individual, of the large number of low energy photons. So basically, what we have here is a kind of high order harmonic generation. So that's why the process has also been dubbed this way. The process takes place simultaneously in many atoms at the same time, given that we have here a spatially coherent laser pulse that drives the atoms in the same way. So they radiate coherently, and the coherent addition of all these tiny emissions lead to a substantial to an attosecond or very short extreme ultraviolet light with substantial energy. It propagates collinearly with the generating laser beam. Both beams come into a second vacuum chamber. They hit a two-component mirror there, the internal part of which reflects the XUV pulse, the external one, the laser pulse. And the two pulses can be delayed with respect to each other with nanometer precision. That's what translates into attosecond timing precision in the time domain. And that's how the one pulse is basically the delay of the or timing of one is controlled with attosecond precision with respect to the other one. So this is the basic apparatus that we can then use for attosecond control and spectroscopy experiments, and I will show you a few examples somewhat later. But before that, I would like to show you how we can use this apparatus for actually characterizing these two important tools for attosecond science, the waveform-controlled fuse cycle laser pulse and the hopefully attosecond extreme ultraviolet pulse, which of course we need to measure before we can really confirm that the duration of this pulse is really in the attosecond range. So to this end, we expose an ensemble of, again, neon atoms to this ultra-short XUV pulse in the presence of the fuse cycle laser field that was previously used for its generation. So thanks to this fact, the two are perfectly synchronized to each other. This is extremely important. And since this strong field is present, the photoelectrons kicked off by the XUV pulse can be decelerated or accelerated by this laser field depending on their moment of release. And due to this deceleration and acceleration, they pick up a momentum. The momentum is changed by an amount that is simply given by the integral of Newton's equation, and this integral yields the vector potential at the instant t, and this instant t indicates the release moment of the photoelectron. So basically, this connects the momentum change with the instant of release. As we see here, monotonically, basically unambiguously and monotonically, and this way maps the temporal profile of a sufficiently short XUV pulse, short enough to be within this half cycle of the laser pulse, where this connection between delta P and the time is monotonic. And this monotonic connection maps the temporal profile of the XUV pulse to a corresponding energy or momentum distribution of the photoelectrons that have been released in this process. We can also refer to this as the streak image of this XUV intensity profile because the method is in close analogy to microwave streak cameras, where a microwave field deflects basically photoelectrons released by femtosecond, picosecond laser pulses. The concept again was pioneered, first proposed by Paul, and he also played a very important role in the first experiments that we performed in Vienna. If the pulse, the XUV pulse, is short enough, significantly shorter than this half cycle, then the streak image of the XUV pulse is hardly broadened. Instead, it's shifted up and down as the XUV pulse is scanned across the few cycle laser pulse. And this set of streaked photoelectron spectra as a function of delay provides full information about both the evolution of the few cycle laser pulse as well as about the temporal profile, intensity profile, as well as chirp of the attosecond XUV pulse. So basically, by a technique or by the very similar approach we are using in frequency-resolved optical gating, we can also retrieve from such a attosecond streaking spectrogram both the temporal evolution of the few cycle laser pulse as well as the temporal profile and chirp of the attosecond XUV pulse down to, meanwhile, 80 and more recently even 70 attoseconds. So just to sum up this part, from our capability of controlling the electric force of light and synchronizing processes under scrutiny to this force, both with attosecond precision, basically the capability of performing measurements on the attosecond time scale arises, and I would like to show you a few examples for how this is working, for how we can actually use these attosecond tools for capturing as well as controlling electron processes. Well, attosecond resolution is required for real-time insight into a truly vast variety of electron phenomena in solids, including ones that are particularly relevant to advancing electronics, to pushing the frontiers of electronics and eventually advancing it to its ultimate limits, such as, for instance, atomic scale charge transport or optical field-induced changes of electronic processes. So if we first address the question whether atomic scale electron transport can possibly be captured in solids, and I wouldn't have asked this question if the answer wouldn't be affirmative. Indeed, attosecond streaking turns out to be ideally suited for capturing electron transport in solids. What we need to do is to shine in an attosecond XUV pulse that kicks off electrons, releases electrons from quantum states of different binding energy, and these electrons propagate, obviously propagate with different speed, and consequently reach the surface at different instants from within their escape depth, which are denoted by D2 and D1 here. And that's the simple formula that determines this propagation delay difference. And now all we have to do is just to shine in a few cycle laser pulse on the surface, and used this for actually recording a streaking spectrogram of both electrons. And this propagation delay or arrival time difference on the surface directly translates or manifests itself in a temporal shift between the attosecond streaking spectrograms simultaneously recorded for the low energy and the high energy electron. This experiment was performed by Andrius Baltuschka and Andrea Cavalieri back in 2007. Meanwhile, quite a few follow-up studies have been performed in a much improved apparatus under the leadership of Reinhard Kienberger. And these follow-up studies have brought to light a very strong dependence of propagation delays on both material choice, system choice, as well as the excitation photon energy, which have been varied here by merely 15 electron volts, so by something like 10%, and this 10% variation resulted in a vast variation of propagation delays. So obviously, electron propagation chronoscopy, as this technique might be dubbed, turns out to be a very sensitive probe of high energy band structure. More recently, Reinhard Kienberger and co-workers have extended this technique to studying electron transport through atomic layers. They released photoelectrons again by an attosecond pulse, and the 4F electrons from the substrate tungsten propagated through an increasing number of magnesium layers put on the surface of this substrate, and the propagation time has been referenced with respect to that of 2p electrons released directly from the topmost magnesium layers. In this way, the propagation difference between these two electrons provided information about the variation of the propagation time of this electron coming from the substrate as a function of the number of add layers. And these propagation time differences have, of course, again been measured by attosecond streaking, and this series of attosecond streaking experiments resulted in a monotonic near linear dependence of the electron transport time through these layers with the number of atomic layers on the surface of the substrate. So this may not be actually very, very surprising, but the experiment fortunately yielded also a much less trivial finding. I would like to show you in the next minute how this experiment has also provided first time domain or direct insight into how abruptly an incident optical field is screened on the surface of a metal. When I'm talking about screening, I'm talking about the normal component of the incident field. Unlike the parallel component, which decays within a few nanometers, which is known as the skin depth, and this is the prediction of just macroscopic Maxwell equations. The normal component, again, according to the prediction of Maxwell's equations, changes abruptly on the surface, just right at the surface. It drops to just a few percent of its value above the surface. And now we are in a position to actually ask the question how abrupt this change actually is. Why we are able to do so? because these propagation times that we are measuring here, of course, depend on the position where this 4F electron starts interacting with the streaking laser field. So if the streaking laser field actually penetrates somewhat deeper, then we expect, and that's what our model calculations show, we expect a decrease in the propagation time because the electron reaches the field and can start interacting with the field earlier. So now we can just do this modeling, and here you see the results for different values of the assumed penetration depth, and its comparison with the error bars of our measurement sets a upper limit on this screening depth, which appears to be less than 3 angstroms. So apparently optical fields, or at least in the near infrared where these few cycle pulses are being produced, near infrared optical fields seem to be screened within one single atomic layer of a metal. The next question I would like to address is whether the physical properties of solids can be modified substantially, instantly, and reversibly by the electric field of light. Why we are interested in answering these questions? Because obviously such kind of changes induced by the optical field might provide routes, might show up ways for pushing the frontiers of electronic signal processing from gigahertz frequencies towards terahertz, and eventually even optical frequencies in the sub-petahertz or possibly even petahertz regime. Now, under which conditions do we or can we expect biggest changes in these physical properties? Obviously, strongest changes can be expected under conditions where we can apply strongest field strength, highest field strength. This is possible in wide-gap dielectrics with few cycle laser pulses, with laser pulses as short as possible. The shorter the laser pulses are, the higher the damage threshold, the higher intensities, the higher electric field strength can be applied reversibly without damage. What we found, and also other groups found, that wide-gap dielectrics under few cycle excitation conditions can be exposed to electric field strength exceeding in strength the so-called critical field strength, which by definition does work on the electron over the lattice constant that is equal to the band gap. This critical field strength is about 2 volt per angstrom in silica. And we asked the question how silica responds to such field strength. And to seek first answers to this question, Martin Schulze, Elisabeth Botschafter, in collaboration with quite a few other co-workers in my group, have exposed silica to a few cycle near-infrared laser pulse at peak electric field strength close to damage threshold. This is about 2.5, 2.7 volt per angstrom, and studied the dynamic changes in band structure, in high energy band structure, and possibly population changes by attosecond absorption spectroscopy. To this end, a time-delayed attosecond X-UV pulse has also been sent into the sample, which promoted electrons from the L shell of silicon to the conduction band. And here you see the attosecond transient absorption spectrogram. So this is the photon energy range within which we have probed the dynamics. This is this energy here, and this is the delay between the fuse cycle near-infrared excitation field and the XUV probe pulse. Here you see a line out of this spectrogram near the band edge, which reveals a very substantial, near instantaneous and almost fully reversible transient decrease in optical density at these photon energies at around 100 electron volts, which seems to actually oscillate in synchrony with the oscillations of the applied electric field of the fuse cycle laser excitation. So this behavior suggests that the dynamics, this electron dynamics that we have created here with the strong field, is governed directly by the electric field of this near-infrared laser pulse and dominated by changes in band structure rather than population dynamics, because real population in the conduction band would definitely survive for a long time after this pulse and would prevent this optical density to return to its field-free value right after the excitation. So this actually suggests that here indeed we have a strong response that is instantaneous, that is reversible. So that's indeed what we are after. But we are actually not really mainly interested in what is the consequence of this response in this extreme ultraviolet spectral range, because it's highly unlikely that future optoelectronics is going to use extreme ultraviolet light for optical signal processing. Most likely we will use visible or infrared light for that purpose. So we would be much more interested in the corresponding nonlinear polarization response of the system at visible and near-infrared frequencies, basically at the same frequencies where we introduced the excitation. And that's exactly what we indeed tackled a couple of years ago. So actually this project has been going on for almost 3 years. Meanwhile, unfortunately, in quite a few cases, this is the time scale of an attosecond experiment, between 2 and 3 years. And I'm happy to summarize for you now the main results of this study, which was again conducted by Martin Schulze, this time with Ann-Kathrin Sommer in collaboration also with Hani Fatahi, who is also here in the audience, and Nick Karpowitz. So what they did here was to send actually basically the same fuse cycle laser pulse, this time through a somewhat thicker, I haven't mentioned before that in the previous experiment the silica sample was extremely thin because the XUV pulse was used as a probe, so it had to be thin enough to transmit some XUV light. That's why it was just something like 100 to 200 nanometer thin. In this case, the sample became macroscopic. It has a thickness of about 10 micrometer, but still thin enough to make dispersive effects negligible. So basically the diffuse cycle laser pulse, in spite of its tremendous bandwidth, is transmitted through this thin plate without any distortion due to dispersion. Now, after this transmission, we send this pulse to the streak camera, measure the waveform with the method I showed you before, and here is the waveform. Now, the next step is to shift this plate into the focus and just repeat the measurement. And here you see the result. So this is again the measured waveform. This time it transmitted at high intensity. And we do see quite some changes. We do see a significant phase shift at the center of the pulse, a positive shift. So the high intensity pulse is delayed. Its phase is delayed on the peak of the pulse. And this phase delay disappears at the end of the pulse. exactly as we expect from the optical Kerr effect. So obviously, we have now time resolved the optical Kerr effect in this experiment. So that's not yet really exciting, but it's reassuring that it gives what we expect. To gain a bit more confidence in this method, we applied it also to a completely different system, to an atomic gas at somewhat higher intensities, so that at the high intensities that we applied, the atoms, in this particular case neon atoms, have been very substantially ionized. And again, we did this experiment at the two different intensities, basically at the low intensity. This is the low intensity reference wave, the green curve, and the high intensity wave is the red curve. Now we see a striking difference to the previous experiment. Here, the phase shift that the high intensity wave suffers due to the ionizing nonlinear interaction has reversed its sign, right? It's not lagging behind the reference wave as it was before, but the phase is advanced, right? So the intense wave is the first. The phase velocity of the intense wave is apparently obviously increased with respect to the reference wave. This is not really surprising if we consider and accept that most probably the freed electrons dominate the nonlinear response. What else would dominate? I mean, they can have huge trajectories, so of course they provide a major contribution to the polarization response of the system, which can be much bigger than the contribution of the bound electrons. So obviously, free electrons, it makes sense to assume that free electrons dominate this response. And we know that free electrons actually introduce a negative contribution to the refractive index. Negative contribution to the refractive index means lowering of the refractive index, speeding up the phase velocity. That's exactly what we see here. And it is also reassuring to see that this speeding up is increasing from cycle to cycle as the density of electrons is increasing during the ionizing laser pulse. So that's very reassuring. Now, what we can also do is just from these two measurements, from measuring the transmitted high intensity waveform and the low intensity waveform in the limit of low dispersion, where we can assume that none of the two is affected by linear dispersive effects, which is a very good approximation in the current experiment. In this limit, we can actually directly determine from these two waveforms the nonlinear polarization response. That's also quite trivial, actually, or that's, I think, quite intuitive. This difference is purely determined by the nonlinearity, because the linear effects are present in both waveforms, right? The linear effects are present both at the low intensity field, the reference wave, the green wave, as well as in the high one. So that cancels out. If there would be only linear effects, both should be the same. But because the high intensity field creates also nonlinear effects, it's not the same. And this difference just provides the direct information about the polarization response. And that's what you see here. So that at first sight is quite surprising. It looks like the electrons became crazy and they oscillate basically completely out of phase, creating a polarization that is completely out of phase with the driving laser field. So now let's just zoom in temporally and try to understand how this can emerge. So let's just assume that, or let's just consider when the electrons are actually released. The electrons are obviously released on the peaks of the laser field. So then the electron is released, but when do we have the maximum of the polarization? The maximum of the polarization response is at the point where the electron excursion is maximum, right? Because polarization is just charge times displacement from the atom. So when is the excursion maximum? At the point where the laser field managed to completely decelerate the electron, which was, say, released here. That's obviously at the next wave crest, where the electron has been completely decelerated. So that's roughly the point when the electron excursion is maximum and the electron starts moving back. So that's why we now understand why this is out of phase. So this is the typical polarization response in an ionizing medium where free electrons dominate the nonlinear polarization response. Now let's get back, after we have now gained confidence in this new method from these experiments, let's get back to what we are most interested in, to silica. And let's calculate also here the nonlinear polarization, just as we did before, from the two waveforms, from the high intensity and low intensity reference waveforms. And here you see the result. So in striking contrast to the ionizing medium, here the polarization response is roughly in almost exactly in phase, almost perfectly in phase with the driving laser field, which clearly sends the message that bound electrons are responsible for this polarization response. But if we take a closer look, we actually recognize that there is actually a small delay of the nonlinear response. And by repeating this measurement at different field strength, we even recognize a very significant, very substantial dependence of this polarization response time on the electric field strength, on the driving field strength here. For a peak electric field of about 2 volt per angstrom, which is roughly the critical intensity, we measure a response time less than 50 attoseconds, way less than 50 attoseconds actually, whereas this response time increases to something just below 100 attoseconds near the breakdown threshold 2.6 volt per angstrom. That's interesting, but what is perhaps even more interesting, if you take a close look, actually this delayed response here at the leading edge of the pulse and here at the pulse center actually turns into a phase advance, right? That's somehow surprising, isn't it? But we can understand this right now if we consider that, or if we recall what the consequence of this phase delay is. The consequence of this phase delay is a net energy transfer from the field into the propagation medium, and vice versa, which is governed by this simple equation, with just simple integral, the electric field, the driving electric field, times the temporal derivative of the polarization. This integral averages, thank you, averages over the laser cycle to 0 if the polarization is exactly in phase with the electric field, and any small phase shift in the one or the other direction makes this integral, also its cycle average value, different from 0. So if there is a polarization delay, then the field starts transferring energy, even averaged over the cycle, starts transferring energy to the propagation medium and vice versa. So now, given that we have measured both the electric field and the nonlinear polarization, we can calculate this temporal, this attosecond varying, or basically attosecond dynamics of the energy transfer in silica near critical fields. And here you see the results. What is obvious that we have an increase in this transfer up to the pulse peak and slightly beyond, which is somehow understandable because the field becomes higher and higher, removes the electron farther and farther away from the nucleus. And obviously, the field has to do work in order to manage to achieve this. Whereas on the trailing edge of the pulse, the field becomes weaker and weaker. So the electron gradually can return to its field-free position. And when doing so, it returns some of its energy to the field in a process very similar to stimulated emission. But obviously not completely. There is a residual energy here, which indicates that some real population has been created that survives for a long time and that leads to dissipation. That's what we don't want to have if we are interested in using this interaction for optical signal processing. What is the useful part of this interaction, of this energy transfer, is the reversible part, which is the difference between this maximum and this residual energy. And what is conspicuous here is that this difference, the reversible part, is much more weakly dependent on the applied electric field strength than the irreversible part. So this conveys the message that with careful adjustment and careful optimization of the electric field strength, we may be able to minimize dissipation, scaling with this, whilst keeping the reversible part that is useful for optical, that can be utilized for optical signal processing at an acceptable level. So that's why I hope that this attosecond polarization sampling may be useful by providing insight into the attosecond energy transfer dynamics of light-matter interactions, may be useful for pushing the frontiers of signal processing and identifying routes for approaching ultimate frontiers. I think I will just skip this and just maybe if I can have maybe three more minutes, just can very quickly through the last part of my talk, advancing our control and insight into electron phenomena obviously requires a few cycle pulses with larger bandwidth for being able to engineer the electric forces of light for improved steering. And we are also interested in much higher peak and average powers for being able to make these forces much stronger. On the one hand, to produce more powerful attosecond pulses, on the other hand, to produce shorter wavelength attosecond light, both for improved scrutiny. So actually, Eleftherios Gouromakis and his team, including Trung Lu, who is also here in the audience, have demonstrated in a series of beautiful experiments how attosecond engineering of the electric force of light is now possible with a multi-channel waveform synthesizer by setting it with a supercontinuum spanning about 2 octaves. They also managed to generate attosecond optical pulses or sub-femtosecond optical pulses consisting basically out of one single half cycle. So this is really spectacular. However, this really spectacular capability of controlling electric forces on a sub-femtosecond time scale unfortunately came at the expense of only moderate field strength, simply because the technology is still based on titanium sapphire based systems limited to, in the few cycle regime, to peak and average power levels of a fraction of a terawatt and several watts respectively. So we believe that advances in attosecond technology demand few cycle light with orders of magnitude higher peak and average power, and this is only feasible with the new broadband amplification technology. And now, according to our conviction, this new technology is likely to be, no, I was too fast, or the computer is too slow, sorry. Somehow there is a big delay here between what I'm seeing here and what's appearing there. Okay. Now, yes, so we believe that this next generation technology is going to be based on broadband optical chirp pulse parametric amplification of visible infrared continua and is going to be driven by sub-picosecond ytterbium disk lasers that are scalable to sub-joule pulse energies and kilowatt average powers. As a matter of fact, we have demonstrated this performance recently in Munich, both with the generation of 100 millijoule pulses at 5 kilohertz at 500 watts of average power, as well as 10 millijoule pulses at 100 kilohertz, which corresponds to an average power of 1 kilowatts. Hani Fatahi, who is sitting here, also demonstrated that this technology is not only powerful, but is extremely reliable. As you can see from this long-term operation exhibiting pulse-to-pulse, short-term pulse-to-pulse fluctuations below 0.5% and long-term drift over 10 hours that is less than 1%. So with such a system that is being scaled to 200 millijoule at a 5 kilohertz repetition rate, according to the calculations and design simulations of Hani Fatahi, we follow this route here to pump 3 optical parametric amplifier channels in the mid-infrared, near-infrared, and visible, and generate several terawatt fuse cycle pulses in all at all 3 wavelength ranges. And if we manage to seed these 3 channels with one and the same couple of octave spanning visible infrared continuums covering the spectral range from 0.5 micron to 2.5 micron, we may be able to coherently combine these 3 outputs through super octave light transients, which may result in the synthesis of all sorts of waveforms with very, very high field strength, including actually near 1 femtosecond pulses with 30 terawatt peak power at a 5 kilohertz repetition rate. These pulses can be optimized for waveforms. This is again just 1 minute and I'm done. Thank you. Was done again by Hani Fatahi and Marcelo Chiappina, this simulation which have showed that optimized waveforms may be able to substantially extend attosecond technology from the current 100, 200 electron volt photon energy range towards kilo electron photon energies, and afford promise for generating 5 angstrom scale isolated pulses with pulse durations in the 10 femtosecond regime, which might open the prospect for imaging atomic scale electron dynamics by attosecond extreme diffraction. So I hope I've been able to show you or to convince you that these synthesized multi-octave optical fields and attosecond X-ray pulses are likely to revolutionize attosecond science and hold promise for observing in real time all motions, including both electronic and structural, in complex systems such as biological molecules and solids, and exploring the ultimate speed limit of signal metrology as well as processing, as well as identifying viable routes to approaching this limit. So I think there is really plenty of reasons to look forward to exciting new discoveries in attosecond science, given that there is plenty of room for exciting discoveries at the bottom. Thank you for your attention.
We'll take time for a question or two, and then there'll be coffee break.
So the slide went by a bit too quick, so I didn't quite follow you. On one point where you had the nonlinear polarization measurement for silica, the question is that the absorption seemed a bit large. Do you open up new channels of absorption, or it was just purely linear absorption, the non-reversible part?
What do you mean by absorb? You are talking about this, I guess.
No, not that. The other one after this, when you showed.
Here. Okay.
Right.
Mm-hmm.
So
say it again.
So the question was that the change in non-reversible part.
Yes.
Right. So was it scaling just linearly or?
No, obviously not. That was the point, right? So thanks for the question. So it scales very, very strongly non-linearly, which is not very surprising if you relate this residual energy density that remains in the system after the laser pulse. Obviously, this relates to real population in the conduction band. This real population can, given the low photon energy as compared to the band gap, can only emerge due to some multi-photon transitions, right? So that's why it's not really surprising that this scales so incredibly rapidly with the electric field strength. And this is good, because this means by slight decrease of the electric field, maybe from the breakdown threshold, which anyway is good not to work very close to breakdown threshold, already helps us to reduce the dissipation tremendously. Whilst the reversible part, which is responsible for the effects that we may be able to utilize for signal processing, is still very comparable. Thank you.
Thank you very much, friends, for fantastic talk.
Thank you.
In your study of nonlinear process, in fact, following out that question, but for the ionizing case,
right.
What was the extension of your excursion path for the electrons? How far the electrons go up and down?
Oh, that's a good point. Well, I can only guess. I think it's on the order of 5 to 10 nanometers.
So if that's the case, what would happen if instead of having a uniform plate, you actually put a bunch of nanowires with the orientation normal to the electric field? So that can interrupt actually the path of the electron. That can lead to huge nonlinearity.
I agree. Would be exciting to look at that. Thank you. Great. Mm-hmm.